Yeah, so last time we saw some key lemmas. So let me just recollect the setup so that it's easier. So say lambda is a young tableau, then we defined two subgroups, P lambda and Q lambda of Sn. So P lambda consists of those permutations which preserves each row of the young tableau, and Q lambda consists of those permutations which preserve each column. And we saw that, in fact, we saw P lambda intersection Q lambda is identity. And then we defined A lambda to be the element of the group ring CSN, where we take the sum over all elements of P lambda, and B lambda is sine of sigma times sigma for sigma in Q, sum of sine, these kind of terms. And C lambda, we defined it to be A lambda times P lambda. Yeah. And then you can define this representation V lambda to be CSN times C lambda. So this is a subspace of CSN, and it's and the action of Sn, and it's a sub-representation, not just ordinary subspace. Yeah, it's an ideal, yeah, a left ideal of CSN, and hence a representation of Sn. So, so we want to show that V lambda is all these. So V lambda is irreducible, and we also want to show that if lambda and mu are young tableaus with different young diagrams, then they are different. They are not isomorphic. So that will characterize all the irreducible representations of Sn. So so last time we proved a lemma. And as a consequence of that, yeah, so what was the lemma? I've written just the corollary. Yeah, so yeah, maybe the lemma is not needed for this, but let's just recall what. So the lemma was if P belongs to P lambda and Q belongs to Q lambda, and C is some element of the group ring such that PCQ is sine of Q times C, then C is a scalar multiple of C lambda. Yeah, that was the lemma. So I mean, it's if and only if, but the forward direction is straightforward. Is the converse which was more difficult. And as a consequence of this this lemma, we got this corollary. So if you take C lambda x C lambda, this element, this satisfies the hypothesis. So if you multiply left by P and right by Q, it's just sine of Q times this element. Yeah? So in particular, you get that this is a scalar multiple of C lambda. So that is how the proof of this corollary comes from lemma. The difficulty was in the lemma. Yeah, so the lemma was somewhat computational. And so in particular, this tells you that C lambda square is going to be a scalar times C lambda. Yeah. So in fact, we'll see that this n lambda is in fact is non-zero. Yeah, some number n lambda. It's actually an integer. Yeah. So I think. Yeah, so but that is a little more difficult to prove. So but nevertheless, it's a non-zero complex number is not going to be difficult. So let lambda and mu be two young diagram. We saw this as well. We can order. We can give an ordering on all the young diagrams of Sn. So we say lambda is greater than mu if the first row of lambda is bigger than the first row of mu, or the first row is same, but the second row of lambda is bigger than the second row of mu, or the first two rows are same, and so on. Yeah, so we give a lexicographic ordering. this partition. Okay. So this lemma I stated, but we didn't see a proof. Its proof is similar to the other lemma I was talking about. Yeah. So if lambda is greater than mu, then this element of the group ring CSN is 0. So A lambda x B mu is going to be 0 for all x in CSN. Okay. So in particular, it tells you that C lambda x C mu is 0. Yeah, because C mu is A mu B mu and C lambda is A lambda B lambda. So it's a term of this kind. Okay. So this lemma together with this corollary will give us this theorem. Yeah. So let's just see a proof of this lemma. Okay. So first of all, to prove this, for all x in Sn, we may just assume that this x is G, yeah, because x in general is some complex linear combination of these G's. So if it is true for one G, then of course it's a ring, yeah. So you can just take the sum over. So it has all the distributive properties, yeah. So we may assume x is G. So that is we have to prove that A lambda G B mu is 0 for all G in G. Yeah. So for all G in Sn. Now this guy A lambda G B mu is 0 happens if and only if this guy is 0. Yeah. So of course, if this is 0, then you multiply by anything, it will remain 0. But if this is 0, you multiply by G on the right, then of course you get that A lambda G B mu is also 0. Yeah. So it's enough to prove this thing is 0, but this is sort of a conjugate. Yeah. So it is like B of G mu. Yeah. So A lambda. So, but I'm trying to reduce it to case that this is something like A lambda B mu prime for some mu prime. Yeah. So A lambda G B mu G inverse is A lambda B mu prime, where mu prime is G mu. Yeah. So this we saw last time. Yeah. If you change this, then so this we saw last time. Okay. Since B mu prime is G B mu G inverse. Yeah, because that's how Q mu works. Yeah, so Q mu prime is basically you take elements of Q mu and conjugate it by G, and that's how you get Q mu prime. Okay. So this further goes back to since Q. So you want rows of mu prime to be so maybe I'll just write G mu. So you want rows of G mu. So G mu is remember G mu is the tableau obtained by replacing the entries of mu by G times G of that entry. Yeah, so you just permute the entries of mu by G. So Q G mu is same as G Q mu G inverse. Okay. So this we saw last time. Yeah. And of course, G mu and G mu prime have the same Young diagram. Yeah, so underlying Young diagram is same. It's just that the tableau is mu and mu prime are different tableau. So again, if lambda is great, so we are assuming lambda is greater than mu. So then lambda is going to be greater than mu prime as well. Okay. So now the tricky part in that was to make an assertion like this. So if lambda, this claim, so if lambda is greater than mu prime, this implies there exist two integers in the same row of lambda and same column of mu prime. Okay. So there exists two distinct integers in the same row of lambda and in the same row of column prime. So the proof of this is again same as in the other claim. You remember we were trying to, so if you had, we had two tableau, lambda and lambda prime, and so there what was the claim? So the we said that yeah, so so is yeah, yeah, so we there the claim was that if G is and if G is not in PQ, in P time capital P lambda times capital Q lambda, then there exists two integers in same row of lambda and same column of G lambda, yeah, or lambda prime, which we call lambda prime. So, and we proved by a contradiction. So what we did was, so we will do the same thing here. Yeah. So suppose suppose there are two. I mean, suppose this doesn't happen. Yeah. So there are no two. There are no two integers in the same row of lambda and the same column of mu prime. So what we'll do is, again, the idea is the same. Yeah. So since I was going to present it last time, I didn't write the argument, but I'll just tell you what the idea is. Yeah. So there are some number of rows in lambda and some number of some number of columns in the first row of lambda. Lambda is lambda one, many entries in the first row, and mu one number of entries in the first. And mu prime has mu one prime number of entries in the first row. So first you consider this, yeah. So 1, 2, 3, 4, 5, 6, 7. Yeah. So suppose these are the entries in the first row of lambda. So of course, all these numbers, they have to be in different columns of mu prime. Yeah, they can't because they are in the same row of lambda, so they have to be in different columns of mu prime. So that tells you that mu prime has to have at least 7 columns. Yeah, but mu prime is less than lambda. Yeah, so that tells you that the first row of mu prime has to have less than 7. Cannot have more than 7 rows. 7 columns, 7 entries. Yeah, so that tells you that, but it must have at least 7. So that tells you that the first row of mu prime has to have 7 entries. Yeah, so the length of the first row is exactly 7. So you get that this is exactly 7, and plus by pre-multiplying, so by permuting this, so there exists P in P1 in P lambda, and so Q1 prime in Q mu prime, such that P1 so what we got is lambda 1 has to be equal to mu 1 prime. Yeah, and moreover, so first observation is that, and so maybe I'll write it here: lambda 1 equals mu 1 prime, and there exists P1 in this and Q1 prime in this, such that P1 lambda and Q1 prime mu prime are have identical first row. Yeah. So the entries are also the same. So I mean, it will be some permutation of 1 to 7 in this case, and here as well. Okay. And of course, then again, if you look at P1 lambda and Q1 prime mu prime, They are again the same young tab. So even if you erase the first column, P1 lambda is going to be greater than equal to Q1 prime mu. Yeah, young tableau, even if you replace it. So you can continue this argument, and if two integers. So we have changed the, we haven't rearranged the rows. We have changed the entries in a particular row by multiplying by P1 lambda. Yeah. So if you started with the property that no two integers are in the same row of lambda and same column of mu prime, that's preserved by these two as well. I mean, it only changed the first row of this, and it changed various columns of Q, but it didn't interchange entries between columns. Yeah. So no two row of P1 lambda, no two integers are in the same row of P1 lambda and the same row of Q1 prime mu as well. So you can continue this way. Same idea. So this was via contradiction. Yeah? Contradiction. So basically you prove the contrapositive. So continue this way to show that the underlying Young diagrams are same. To show lambda actually equals mu prime as Young diagram. Yeah. So probably the right way to write it is P and Q prime, and then you can say about Young tableau itself. So there exists so maybe I'll just write as Young diagram. Yeah. Meaning I don't care about what the entries are. But by this way, you'll get that the second row of lambda and the second row of mu prime are have the same length and so on, and you carry over these arguments, and you'll get that in particular that the lambda is same as mu, yeah, which will contradict the hypothesis. So once you have this claim, so is this okay? I hope this is okay, because last time I went over this argument. Yeah, is this fine?
Yes.
Yes. So it's the same argument. It's just that you have to do it again. Yeah. So now consider. So now assume that this claim is. So now we know why this claim is true. So let T be the transposition which interchanges these two integers. Yeah. Then T of course belongs to P lambda, and T also belongs to Q mu prime. Okay. Then you will get that A lambda B mu prime is same as A lambda. So remember, T is a transposition, so it has order 2. So I can put in T times T here. Yeah. But what is A lambda times T? So that is just A lambda, right? So we saw that if you pre-multiply A lambda by P or post by an element of P lambda, or post multiply, you keep it A lambda. So you get A lambda, but T times B mu prime will change by the sign of T. Yeah. So sign of T of course is minus, because T is a transposition. So you get A lambda B mu prime is minus A lambda B mu prime, which is same as saying that A lambda B mu prime is 0. Yeah. And that is what we had to show. Okay, so so this hence the lemma. Okay, so I hope the proof of this lemma is also clear. So basically, it's the same idea, except that you apply it in this setup. Okay. So these are the two lemmas which we'll use to prove our result. Okay, so remember the statement: C lambda x C mu is 0 if lambda is greater than mu, and the other thing is C lambda square is some n lambda times C lambda for some n lambda a complex number. Okay, so now the main theorem. Let lambda be a young tableau and v lambda be this guy, which was there as well. Then we want to say that v lambda is irreducible. Moreover, if mu is another young tableau with different young diagram than lambda, then v lambda and v mu are not isomorphic. So these are the two statements we want to prove. Okay. So let's try to show v lambda is indeed indeed irreducible. Yeah. So let yeah, little thicker. So let W contained in V lambda be a sub-representation. So we want to show that W is either whole of V lambda or 0. Yeah. So you know how things work here. Yeah. So W is a subset of V lambda and is a sub-representation. So W is I mean it is a it's a submodule of CST, and V lambda is an ideal. So it means W is also an ideal. Yeah. But there is another thing. So you know every I mean it's W is contained in CST, yeah, as a sub representation and so on. But you know this is semi meaning every there is a complementary sub representation. Yeah. So so there exists W prime in CST such. So I've changed from SN to ST because the book was using ST, but it doesn't matter. Yeah. So there exists W prime in CST such that W plus W prime is equal to CST. Yeah. And W prime is a sub representation. Yeah. So this is something which we saw long back. Yeah. So if you take a sub representation, then there is a complementary. And this is how we prove that every representation you can write it as product of irreducible representation. Yeah. So W prime is also going to be a submodule of CST. So W prime is also a left ideal, left CST ideal. Yeah. So it's a module, but it's contained in CS. It's a left module, but it's contained in CST. So it's an ideal in fact. Yeah. But yeah, so we want to show that W is contained in and W is either V lambda or 0. Yeah. So let's try to analyze what is W. So let's multiply W by C lambda. Okay. So what can we say about C lambda times W? So so note C lambda times W is of course contained in C lambda times V lambda. Yeah. Which of course is equal to C lambda C ST C lambda. And what is this guy? So remember, if you sandwich any element between two C lambdas, you get a complex number times C lambda. Yeah. So this is nothing but C times C lambda. Okay. So this becomes a one-dimensional subspace. One-dimensional subspace of CST. Is that okay? So this is where we are using the lemma from the corollary. Yeah, so by curl. Okay. So C lambda x C lambda is some constant times C lambda. So it is actually a one-dimensional subspace. So that tells you that this implies that C lambda W is either C times C lambda is C times C lambda. So it's either this subspace or it is zero. Yeah, one or the other. So if C lambda times W is C times C lambda, then I want to say that W must be whole of wheel lambda. So why is that? Yeah, so you C lambda times W, you already get C lambda in it. Yeah. So if I want to get any V lambda, so if that X belongs to V lambda, then X is Y times C lambda for Y in CST. And that is the definition of V lambda, right? So yeah, so Y times C lambda is so this implies there exists W in W such that C lambda times W is C lambda. Yeah. So now Y times C lambda is equal to so yeah, so is equal to Y times C lambda times W. Yeah. But what is this guy? This is in CST. Yeah. Y times C lambda, and W is W is in capital W. Yeah. So so W is a submodule. Yeah. So this tells you that the action of this on this is still in W. So this belongs to W. Yeah. Which implies Y times C lambda is in W, which implies V lambda equals W. Okay. So so if C lambda W is happens to be the this scalar times C lambda, then we get that W has to be the whole of V lambda. Is this okay so far? Yeah, so we are just trying to work out the two cases. So either if it is C times C lambda, I'm just multiplying here on both sides by CG. Yeah, so maybe instead of doing this, maybe one could have done directly by saying that this implies C ST C lambda, which is some collection of elements in ST times W is equal to C ST C lambda, yeah, which is V lambda, and this of course this of course is contained in W. Yeah. Okay, so that proves that V lambda is also contained in W. That's what this element-wise argument is. Okay. So that takes care of the case when C lambda W is this one-dimensional space. What happens if C lambda W is 0? Okay, then yeah. So then so C lambda W is 0. Then we want to show that W is 0. In fact, yeah. So yeah, so this is where the other factor will come in. Okay, so let's see. So W plus W prime. Yeah. So So W is also a quotient of CST. Yeah. And yeah, so this also implies that V lambda times W is 0. Yeah, because V lambda is like element. I mean, any element in V lambda is something times C lambda. So V lambda times W is 0. Yeah, and yeah, so that should be so which implies yeah. So I want to conclude W is 0 from here. Yeah, so okay, so maybe think of it this way. Yeah, so this yeah, so the point is this this is as a product of rings. Yeah, so you have this CSD is W plus W prime. Yeah, and of course so you take identity here, then you can write it as W uniquely, in fact, as W plus W prime for W in W and W prime in capital W prime. Yeah, uniquely. Now, if you think about it, W E square is E square is E implies W plus W prime whole square is also E. And what is the square of this? So if you multiply element of W, it lands in W. Yeah. So it's W square plus W prime square plus W times W prime plus W prime times W. Yeah. Something like this. But these two are these two are in this is an intersection of W and W prime. Yeah. So and yeah, so why is that? So 1 second. Yeah, so this is not a commutative thing, so I have to be careful. So what I want to show is that W square, so the W and W prime are idempotent. Yeah, so that this works out.
Excuse me, sir.
Yeah.
So can we use the fact that E is equal to W plus W prime?
E is equal to W plus W prime.
Yes, sir. Like for first time, like W prime, we substitute. It's basically because W prime, capital W prime is an ideal, then it's already in W prime, the first term. But then if we substitute W prime by E minus W, then we'll get it's in W as well.
Sorry. So what you are trying to? So you are trying to prove that W and W prime are idempotent, yeah?
Yes, that's what I'm trying to prove.
Yeah. Tell me again. So maybe
yes,
some W plus W prime. Oh, maybe you are trying to say use this identity. Yeah. So E times W is W plus W prime times E times W. Yeah, this is what you're trying to say?
Yes. But not directly this, perhaps first if we can show that W prime times W equal to 0.
Yeah, but why is that? That is what I'm trying to argue.
Yes. For that, sir, W prime times W is already in the ideal W.
W plus
W prime times W. I'm just looking at that.
That is in the ideal W. That is okay. Yes. W prime plus W times W is in ideal W, as W is left ideal.
But now W is E minus W prime.
W is that is the identity. Yeah, W is E minus W prime. Yeah.
And this thing is basically inside W.
And
W prime. Yeah.
And this thing. So this is. And this thing is inside. Yeah. So this is equal to W prime minus W prime square, which of course is in W prime. Yeah. So this implies W prime W is belongs to W intersection W prime, which of course is 0. Yeah. So and similarly the other term W times W prime. Thanks. Yeah. This is what I was trying to So those who work, yeah. So in commutative case, it's not an issue, but here one has to be careful. Yeah. So this tells us. So now we can use that argument which I was trying to allude to. So this tells us that W plus W prime whole square. And this was Snehin, right? Thanks, Snehin. W plus W prime whole square is W square plus W prime square, yeah, which is identity. And the uniqueness tells you that this belongs to W and this belongs to W prime. Yeah? So by uniqueness, you get that W is equal, W square is equal to W, and W prime square is equal to W prime. Okay. So what you get is that this identity is as product of rings. Okay, so from here, so you have that. So W, you can think of it as so W is basically CST times W. Okay, so this is so this implies that W is going to be this guy. Okay, because I mean this is the splitting. Yeah, so you get that W is this guy, and yeah, so if V lambda times W is 0, so this tells you that so W belongs to W is contained in V lambda. So this tells you that W times yeah. So yeah, so the point is if W was non-zero, then W yeah. So yeah. So what do I? So this yeah. So W square is in which is W is yeah. So W square is in V lambda times yeah. So is in W, which is same as W square, is in V lambda times W, because you know W is in W and W is in V lambda. So since W belongs to V lambda, which W belongs to W, which is contained in V lambda, which is 0, which tells us that W must be, so it's generated by 0, yeah, so that means W is 0. Okay, so that sorry, this only proves the half of it, the first part of the statement, yeah. So that completes the proof that so hence V lambda is irreducible. Okay, so we have shown that there are two cases. C lambda times W is either C times C lambda or it's 0. Yeah, so if it's C times C lambda, then W happens to be equal to V lambda, and if it is 0, then W happens to be 0. Yeah, so that is what it says, that V lambda is irreducible. Yeah. Now the second thing is to show that if V lambda and V mu are not isomorphic, then if lambda is different from mu, then it's not isomorphic. The underlying Young diagrams are different. So if so for the second part, so if there are two Young diagrams, of course, there is an ordering, yeah? So one has to be smaller than the other. Yeah, so let's assume lambda is bigger than mu. So may assume lambda is bigger than mu. Yeah, and then we will use the other lemma, which we saw here. Yeah, then that tells you that C lambda x C mu is 0. Yeah, so then this implies C lambda for all of this. Yeah, so C lambda CST C mu is 0. Yeah, which implies that so this guy is V mu. Yeah, so this implies that but C lambda V lambda is not 0. Yeah, in fact, this is C times C lambda. Yeah, because this is C lambda CST C lambda. Yeah, so this is the whole of C times C lambda, but this guy is 0. Yeah, so V mu is not equal to is not isomorphic. V lambda. Okay, so there's still a bit of argument, I think. So why is C lambda V lambda non-zero? So we know that it has to be contained in C lambda, or it has to be non-zero. Yeah. So okay. Yeah, so C lambda. Yeah, so basically, yeah, so V lambda is also, I mean, V lambda plus some guy, W prime, is going to be CST. Huh? And then V lambda is, then again, you will get some elements here. So So an idempotent for V lambda, and that has to be some multiple of C lambda, yeah, because yeah, so yeah, so we I mean so in fact square root n lambda C lambda, if you, so you'll get some element, but that if you square it, then you get n lambda. So you have to divide it. Yeah, but I haven't said why this is non-zero. But yeah, that part. So explicitly we don't need it. But say so there is an idempotent corresponding to V lambda. Yeah, so let's call that idempotent X. Yeah. So so V lambda is also CST X, but it is also but it's also CST C lambda. Okay, so that tells you that X and C lambda are scalar multiple of each other. Okay, and but C lambda is non-zero. So X, I mean, if C lambda V lambda happens to be 0, then X must be 0. Yeah. So since X is not 0, that tells you that since C lambda is not 0, X cannot be 0. So that tells you that C lambda V lambda is non-zero. Okay. So that that will complete the proof that C lambda V lambda is different from V mu is different from V mu. Okay, so it also proves that C lambda square with is n lambda C lambda, then n lambda, this n lambda guy is non-zero. Yeah, it's non-zero. So in fact, that n lambda is I mean. You divide by square root of n lambda, then you what you get is this idempotent X. Okay. So this is how the argument goes. Yeah. So remember, V lambda corresponds to an idempotent. So it's the same kind of argument. Yeah. Like here, W corresponded to an idempotent, and we from the argument we saw that V lambda W is 0. So here also V lambda will be 0 because it's a sub-representation. If this happens to be 0, then we get that V lambda itself is 0. But V lambda is non-zero, that we know. Yeah, because C lambda is a non-zero element. So C lambda, remember, has identity plus something. Yeah, so it's a non-zero element. So of course, it ST times C lambda cannot be the zero ring. E times C lambda at least belongs there. Yeah. So that completes the proof of this this thing. So in particular, so let me just V lambdas are all the irreducible representations of CST, where lambda varies over all the Young tableaus, Young diagrams. Okay, so of course, you know, the number of irreducible representation of ST is in so number of irreducible number of distinct irreducible non-isomorphic irreducible representation of ST is is in bijection with conjugacy classes of ST, classes of ST, classes of ST, which of course is in bijection with and this is in bijection with Young tableaus, Young diagrams. Yeah, and for each Young diagram, we have at least, so you fill in and you get a irreducible representation. And if you take different Young diagrams, then they give you and fill it and you get different irreducible representation. So we get that, enough irreducible representation. Okay. So these are so these are all and hence enough hence these are all. Yeah. So from here you can also deduce that V lambda, and if also if so from here you can deduce that V lambda and V lambda prime are isomorphic irreducible representation if lambda and lambda prime have same Young diagram, meaning even if the tableau is same, the tableau is different, you get an isomorphic representation. Why is that? So lambda and lambda prime have the same underlying Young diagram. Yeah. So V lambda, if you think about V lambda prime, it's certainly not isomorphic to all the other irreducible representation. If you take some other Young diagram, which is different from lambda prime, then it's not isomorphic. That's what we saw. So but it's irreducible representation, so it has to be isomorphic to one of them, and then what remains is V lambda. Yeah, so it has to be isomorphic to V lambda. Okay, so by exclusion pigeonhole principle, we can say that it has to be, these two are going to be isomorphic. So since V lambda prime is not isomorphic to V mu for mu different diagram, and it being irreducible has to be isomorphic to V lambda, one of them, and the only one remaining is just V lambda. Yeah. Okay. Is this clear, everyone? So I hope this proof also towards the end also made sense. Yeah, and this argument. Any questions or comments?
Sir, please go through the part where you prove that mu and V mu and V lambda are not isomorphic once again. Like I got the part that they are not equal, but why are they not isomorphic?
They are not isomorphic because you see there are two representations, yeah, V mu and V lambda. Okay, and so if so this as C lambda is there is an action of so C lambda induces induces an endomorphism of the action, induces an endomorphism of V lambda and V mu. Yeah. by the representation. So let's say rho lambda c lambda belongs to this, and rho mu c lambda also belongs to end v mu. Yeah. So if they are going to be isomorphic, these two are going to be, conjugate at least. Yeah. But you can see that the C lambda acts via something non-zero. It's a non-zero endomorphism. Yeah, C lambda times V lambda is non-zero, whereas C lambda times V mu is the zero map.
Okay, sir, got it.
Yeah. So that is where we are using it. So yeah, so maybe this implies this is what I meant. Yeah, this is zero. But C lambda times V lambda is not. So, you think of it as the action is given by C lambda is sort of made of elements of ST. Yeah. So the action is given by various elements of ST. So that is how this left module is. So these left modules are not isomorphic as well. Yeah, because if they are isomorphic, the annihilators have to be same and so on. Yeah.
Yes, got it.
And so one contains C lambda, the other doesn't contain C lambda. Any other questions or comments? That is why we were trying to prove that this is actually non-zero. Okay. So finally, one last thing which I want to finish so that this discussion is done, and next time we'll start. So this will not take too long. Sorry for going over. So see, we know that C lambda square is n lambda times C lambda. Yeah. Then for some n lambda, we have an expression for this n lambda. N lambda is so I have written this formula upside down. Then dimension I'll write it as I n lambda is d factorial over dimension v lambda. Okay. And yeah, so so I don't know. So I think dimension v lambda should divide d factorial, but I think I saw something like that. But anyway, that is not the assertion of it. So why is this true? So so consider this this map F from CSD to CSD, which is multiplication on the right by C lambda. Okay. So it is of course a linear map. And in fact, it's a linear map of representation because, it's the representation action is on the left. Yeah. So it's SD equivariant. So if you take W to be kernel F, it's actually a sub-representation of CSD. Okay. And so, of course, this as a vector space, you can write it as as a kernel of F plus image of F. Yeah. So so if given any endomorphism of a vector space, you can always write it as the domain as kernel of the endomorphism plus the image of the endomorphism. Yeah. So that is what I have done. It comes from the short exact sequence. Yeah. So CSD to image is V lambda in this case. So this is surjective and the kernel is W. Yeah, so this is a short exact sequence. And of course it splits not only as vector space, but actually as representation because we saw that happens. Yeah. So from this picture, you get that CSD is W plus V lambda. And if you think about what if you want to look at F, how does F behave with respect to this decomposition? F restricted to W is 0. And what happens to F restricted to V lambda? So V lambda is CST times C lambda, and you're multiplying by C lambda on the right. So it's just multiplication by N lambda. Yeah, since if X belongs to V lambda, then X is Y times C lambda. So F of, which implies F of X is Y times C lambda square, which is C lambda square is N lambda times C lambda. So N lambda times Y C lambda, which is N lambda times X. Yeah. So Fx is just multiplication by N lambda. Okay. So that tells you that, so if I want to compute the trace, I'll take a basis of W, take a basis of V lambda, and then compute, and that will give me a basis of CST, and then compute trace. Yeah. And then of course the trace, so for the W part, you'll get zero matrix. For this V lambda part, no matter what basis, it's just multiplication by N lambda. Yeah? So it's going to be N lambdas in the diagonal. So the trace of F is N lambda times the dimension of V lambda. Okay. So that's one way of computing trace. Another way is to think about, so you take the basis as the elements of ST, yeah, the standard basis for CST. Okay. So if you think about C lambda, how does C lambda looks like? Is this guy, yeah? So it has E plus some terms, identity of SD plus some terms which does not involve E. Yeah, in fact, we know what exactly it is. It's of this form. So now if I consider this F applied to this basis element G, so basis is elements of ST. Elements of ST form a basis. So if I apply F to G, then this is G times C lambda becomes G plus some terms not involving G. Yeah, so it's some linear combination of other elements of ST. Yeah, so that tells you that in the diagonal entry you'll get 1. So in the matrix of F of F with respect to basis ST, the diagonal entry is 0. Diagonal entry is 1. Entries are all 1. Because the diagonal entry corresponds to where what is the coefficient of G. Yeah. So you get that the trace of F has to be the size of dimension of CST, which is the size of ST, which is the factorial. So so these two numbers must be same. So that tells you that dimension of V lambda times N lambda is d factorial. Okay, so that completes the proof of this proposition, and maybe so I was thinking of giving you the formula for character today, but we'll do that tomorrow. Okay, so sorry for going over. I didn't anticipate so many breaks.